We've been looking at longitudinal lately, and we're about to shift gears and look at lateral directional. And longitudinal, an airplane is essentially a two-dimensional object. Okay. It doesn't couple with the other modes of motion. And so that makes it somewhat simple to evaluate. However, longitudinal is a pretty important mode of motion. And what you're going to find when and if you get in the real world of airplane design, that they never get it right the first time. Okay, and so the airplane gets to flight test and it doesn't meet all the requirements. And so the company's going to depend on you as a flight test engineer to come up with some fixes. And the answer is not, well, redesign the whole airplane. Not at that stage, because if they do, they'll lay you off first. Okay, so that's not the answer. The answer is not redesign the airplane. The answer is fix it. And so you start by fixing the most simple things ways you can do about it. And that's what we're going to talk about today, okay? Some methods for improving the longitudinal stability control of the airplane. Well, we said that the most aft limit was normally determined by stability, the forward CG by control power, and of course, we said when we flew into ground effect, the downwash off of the main wing affects the angle of attack at the tail, and so that may very well set how much up elevator we need. And of course, the CG location is going to affect the ability of the trimming device to trim out longitudinal control forces. And we said that the FCG was critical for high-speed trim. The forward CG is critical for low speed and large flap deflections. So once the airplane has reached the flight test stage, how do we go about improving longitudinal stability control? Well, there's several things we can do. And generally we want to start out with the simplest fix. You know, the old KISS principle, K-I-S-S, keep it simple, stupid, which is what that stands for. So that's what we want to do. We want to start with the simplest things and work up to the big things, you know, the final thing being, yeah, well, redesign the whole airplane, you know. But like I say, that's not going to happen or you're out of the job. Fixes that would require the least change of the airplane are the ones that we would try first. And we might call them gimmicks, or to get real sophisticated, we can call them simple stability augmentation systems. Okay, you know, that's probably a more acceptable term in today's world. And in these systems, we don't really change the stability control, but we try to fool the pilot into thinking we have. Okay, well, these early simple fixes will increase control force maybe, but they won't change the location of the stick-free neutral point. They just make the pilot think we've changed it. Okay, so that's probably the first thing we're going to look at. We'll do that. And it's worth noting that these systems work for both, or some of them at least, and I'll tell you which ones, work for both reversible and irreversible control systems. You know, depending on the kind of airplane you're dealing with, you may have one or the other. was rather interesting that several years ago, the Air Force was trying to build a new trainer to replace the T-37, and they bought an airplane called the T-42, I believe it was and it was built by the folks at, well, Republic, I guess, was the company, and it looked a little bit like a baby A-10. And they had a couple of them out at Edwards. Trouble was, no one at Edwards remembered how to do a reversible control system. You know, how to go about flight testing. So anyway, you all will understand that. So we're going to take a look at these things. Well, several different. First thing we probably do is springs. You know, you can get a spring, you can add force with the spring. And the first one we'll look at is the stick centering spring. And this spring tends to center the stick and add a force increment which depends upon how far the stick is displaced. If we can see, here's an example of it. Notice that, you know, you have an equal, you move this bell crank and you generate force in either direction by applying a force to the stick. Well, that improves the control force at low speed for both static and maneuvering stability, but the effect diminishes with an increase in airspeed. If you notice from our plot of elevator position, when we did longitudinal stability, what did that plot look like as the speed increased? Got pretty flat, didn't it? Okay, so at high speed, it doesn't take a lot of control movement to change the airspeed. So that's, you know, would be kind of a limitation on this particular thing. And a problem with centering springs for a reversible control system is that the control stick doesn't trim at the same position for each trim airspeed. And of course that would then introduce a force bias from the centering spring. However, that's not a problem for an irreversible control system, because the stick can always come back to the same position for that, because, you know, you're not connected directly to the control, or not mechanically anyway. So the stick can always come back, and as a result, you find centering springs used in irreversible systems quite often. That's where you know, one way to get the force, and you can, you know, put things to increase the force and decrease the force by stretching the spring. The other thing these things work well on are for controls like ailerons or rudders that always come back to the same position in flight. And so you see them use, centering springs used quite a bit for those kinds of controls. Well, here's another spring. It's called an elevator down spring. And what it does, it makes the elevator float down. Notice that it's just a spring on one side there. And, you know, as it compresses, what happens to the elevator there? It goes down. Okay, now, how do we, if that happens, you can see if you pulled against that you're going to get a force increase, right? What about on the other side of the trim?
Spring acts in both directions.
Now, what's going to happen if you've got a trim elevator position? Does this spring affect that trim elevator position? Doesn't, okay? So, in order, if you put one of these things on, you're going to have to make the elevator float back to its original position for trim, you're going to have to change deflect the trim tab, which isn't shown here, okay? You're going to have to deflect it more. Well, then, above trim, that trim tab's going to dig in. So below trim, you're working against the spring. Above trim, you're working against the aerodynamic force created by the trim tab. Does that make sense? So that second bullet there says, with the spring installed, additional trim tab deflection must be added to cause the elevator to assume its original trim position. And that causes a stick force gradient then at all airspeeds, okay? And since the force increment isn't a function of stick position or normal acceleration, the downspring doesn't improve maneuvering stability. So if you're going to use a downspring, and a lot of airplanes do, you're not going to improve maneuvering stability a bit. You'll improve longitudinal stability, but not maneuvering stability. Which brings me to a point. Years ago, the federal air regs did not have any requirement for maneuvering stability. So downsprings were used a lot. Trouble was they developed several airplanes in that time frame that didn't have any maneuvering stability to speak of, any stick force per G. And that resulted in a lot of airplane breakups in flight due to people getting in thunderstorms and, you know, coming out the bottom and looking at the earth and honking back on the control with no maneuvering stability, and watch the wings go away as they continued their journey to the earth, okay, a big smoking hole. So the FAA changed the rules after several of those and added a requirement for maneuvering stability. But up until that time, you go back to the older rules, back to CAR3 and early variants thereof, there were no requirements for maneuvering stability. So a downspring got used a lot in those days because it improved the apparent, doesn't change the maneuver or the neutral point at all, but it makes the pilot think you have. Okay, because it gives the pilot control force that he didn't have before. I have seen these used back as far as the neutral point, with the CG on the stick fixed neutral point. So it doesn't improve maneuvering stability. And it makes the phugoid go bananas. Okay, you may have a stable phugoid. Again, there's no requirement, go read the rules, no requirement for the phugoid to be stable in the FAA regs. Still today. So a downspring will cause the phugoid, drives it towards instability. But it can only be used with a reversible control system. You know, you just hook that spring to a down cable essentially, and you know, but you're probably going to have to add more nose down trim in order to counteract the force of the spring. Well, another device is called a bob weight. And a bob weight is a mass placed, in this case, forward of the center of gravity, here somewhere. It's a mass. And out on this arm does the same thing that the downspring does. Causes the elevator to float down. Again, You got to float it back to the trim position, so you have to have more trailing edge down trim tab. And you get the increase in stick force slope by one, lifting the weight, okay. Pilot's, when he pulls back on the control, has to lift that weight. And when he pushes forward, he's working again against the further deflected trim tab. Neat thing about this is, for maneuvering, what happens to that weight? Let's say you're at 2 G's. Yeah, that weight was 5 pounds originally. What does it weigh then? 10 pounds, right? So bob weight increases maneuvering stability also. And so a lot of airplanes, when the FAA come out with that requirement, started putting bob weights in rather than downsprings. Well, what's wrong with it? And, oh, by the way, I forgot to mention, helps damp the phugoid because the weight has inertia and it's going the other direction when you're doing the phugoid oscillation. Okay, so it helps move the elevator and damp that phugoid motion out. Great. What's wrong with it?
At a high bank angle, it's not flying at its
weight.
It's still, you have to get very steep for that to happen. Okay.
It's weight performance.
It's weight, that's one thing. Weight, you don't want to add weight to an airplane, right? That may be somebody's suitcase that gets left behind because of the weight being in there. You can't carry that extra suitcase.
Just out of curiosity, what is a common weight for a bob weight? Typical like airplane returns?
It may be 5 pounds, okay? 5 to 10 pounds wouldn't be out of hand. So at 2 G's, if it was 10 pounds, that's 20 pounds, But the thing of it is, adding 10 pounds to an airplane, which you want to keep light, is something you probably don't want to do. That's one thing. There's another one.
The flexibility issue, like a spring?
Well, it's not flexible, but it has inertia. And so if you're in turbulence and the airplane is doing this, what's this thing going to do to the feedback to the pilot in the control system? He's going to be sitting there feeling this sort of thing, okay? Due to the turbulence. The control is going to be hitting back at him, so to speak, because of the bobbling. Well, there's some ways to avoid that, and we'll take a look at them here. Here's the 2 drawbacks. Stick pumping, feedback into the control system in rough air, and second one, of course, is added weight. We don't like to add weight. Here's a way to possibly fix that. And this sort of thing was used on airplanes that, like fighters in World War II, they used this kind of an arrangement where we have a weight up here ahead of the CG. This is probably the heavy weight. And here after the CG, we have one that's opposing. So what's happened when you're in turbulence there? It damps it, or opposite, and so it damps it out, see? So that's the reason for doing this kind of arrangement. But now you can see, hey, you've added a lot of claptrap to the airplane, so to speak. Okay, you've added even more weight in order to fix it. But bob weights, have found use in fixing problems. Again, this is something we add, right? We haven't changed the airplane design at this stage at all, right? All this stuff is inside. Well, another thing, if you don't want to add too much weight, tie the bob weight to a spring. put a downspring in along with the bob weight. And so you keep the overall weight down, okay? So you're reducing the weight penalty while you have the advantage of the bob weight for maneuvering and for helping with the phugoid. Okay? And so we can tailor the size, the bob weight, and the spring constant, and get stability levels to what we want without adding too much weight, okay? And it can be designed to meet space limitations. Let me show you one that I did. Essentially, this was in my first job as a test pilot. This is the firewall of the airplane. Cockpit floor here, you know, control yoke. Here's the instrument panel. And so we put an aluminum tube between the rudder pedals, tied the spring to the cockpit floor and the spring to the weight around the pulley, and tied it to the control yoke. Worked, and it didn't take up much space. So you have to sometimes get pretty creative. However, if you don't get there and you already have a weight problem and don't want to add much more weight to the airplane, what would be the next, or what you tried just didn't quite make it with springs and weights? What might be the next approach? Tabs on the elevator. Again, we're trying to keep change to a minimum at this stage because we've got a flying airplane here. It may not meet the rules, but it's a flying airplane, and so we don't want to go back to a clean sheet of paper design. We want to fix what we've got. We kind of like what we've got, it just doesn't quite meet the rules. So, next thing we might do is go to a trim tab. To fix the problem. Several varieties of elevator trim tabs that can be address stability and control problems. First one is called the balance tab. That's what the Cherokee 6 has. Cherokee 6 has a balance tab. A leading balance tab, because as you increase the amount of up elevator, the tab moves farther than the elevator. And what does that do? Tends to drive the elevator back to its original position. So the pilot has to hold the force, right? In fact, if you don't put a leading tab on an all-flying tail, the pilot will have no control force. And he won't be able to really trim the airplane either, all right? So you have to have a tab of some kind if you have an all-flying tail or stabilizer. So we'll look at balance tabs. Another tab that's out there, it's called a servo tab. And a servo tab, the pilot actually moves the tab, and it moves the elevator. That's what a servo tab really is. Now, the magazine writers in recent years have got this all screwed up, okay? Because if you read the magazine, it'll tell you that a Cherokee 6 has an anti-servo tab. What in the hell does that mean? Okay? Well, it's really a leading balance tab. There are two types of balance tabs, and we'll talk about both of them in a minute. Third type is called a spring tab, and again, we're going to talk about all of these, and then the spring-loaded tab. Well, let's talk about balance tabs in more detail. It's a geared tab that can be made either to lead or lag the elevator movement. Let's take a look here. Here's kind of how you do it in simple-minded mechanics. It's a leading tab up there on top, so you can do this on an elevator in addition, a stabilizer elevator arrangement in addition to just an all-flying tail or stabilizer, okay? Here's a lagging tab. Notice the difference between the two. If the forces are too high, poor pilot can't move the control, maybe you want to put a lagging tab on. Again, we're still talking at this stage, we're talking about reversible control systems. Remember, irreversible control systems are a relatively new thing. I was born at the beginning of World War II, and in World War II we had no airplanes with irreversible control systems. None. Nada. They were all reversible systems. And so we had to use some of these techniques for the pilots to be able to even fly them. Okay? Because the control forces on a big airplane are just too high. You know, the aerodynamic loads are way out there. But this is a leading and a lagging tab. Well, we might even today still want a lagging tab somewhere on a given control. What might be one that we would want one on? Anybody think of one? Ailerons is a possibility. How about the rudder on a multi-engine airplane when you worry about one engine out? You know, poor old pilots, you know, by the time he flies very long on one engine, you know, the leg is, looks like jelly. It's shaking so much, all right, from holding the rudder in to keep the airplane from rolling over on its back. I wish we could, wish we had a multi-engine airplane we could do a multi-engine flight in. We would look at some of the multi-engine problems, and that would be one. Well, the leading balance tab is effective for fixing longitudinal control problems because what does it do? The leading tabs make the elevator want to float back to where it was. So the leading tab actually does change the stick-free maneuver point and stick-free neutral point, okay, because of the fact of this. Actually shifts those further aft than they would have been if you had the same size elevator. It reduces that tendency to float, and as a result, actually shifts the stick-free neutral point aft, and it reduces the floating tendency. It also helps the dynamics, because what's going on in the phugoid is that the elevator is floating. As you slow down and speed up, it floats back and forth, okay? So this thing tends to make it want to stay where it was. Yes, sir?
So is the primary point of the trim tab to I guess, is it to increase the elevator effectiveness, or is it to bring the elevator back?
It's to bring it to a trim position. And so when you have a leading tab, it's trying to force it back to that position, right? Because if you deflect it, it deflects more, trying to force it back.
It's about the moment then.
Yeah, okay? So, stick-free maneuvering stability is increased with this leading tab, since the tab input to the control system is a function of the elevator deflection. And what happened in maneuvering? We had more deflection, right? Due to the rotation, we had to have more deflection to get the additional G. Here's an example. Took this out in Arizona at the forget what the name of that museum is, but this is a Corsair from World War II. Notice that, look at this rod here connected to this tab. What kind of a, based on the other, what is that? That's a lagging tab, right? It's a lagging tab because the elevator forces on the Corsair obviously were too high. This is a flight test fix. This wasn't designed in there. It's a flight test fix. They got that airplane and they went out to fly it, and the pilots couldn't maneuver it, come back and said the control forces are way too high. All I can do is about fly straight and level in this thing. And so the smart flight test engineers told the design group, we need a lagging balance tab. And so they designed one and put it in. Yes?
Did the Japanese Zero have any of these fixes, do you know?
I have not, there are so few of those in the world these days that I've not had a chance to see one, okay? I mean, up close and personal, so to speak. Nice thing about this museum, which is north of Phoenix, is that you can walk in and along the airplanes and see all of these fixes. And when you go to a museum sometime, look for this stuff. That's why museums are there. They're give you an ideas about what can be done. Because somebody else has thought about these kinds of problems and dealt with them. Here's another little airplane. This one was designed and built not too far from here, as a matter of fact, down in Fort Pierce, called the Miko. And I'm going to show you some stuff on it here in a minute. Well, we talked about the balance tabs, leading and lagging. And I mentioned the servo tab earlier. Servo tab does this. This is a pivot point. It doesn't move the elevator, it's just there so that you have a way of moving this arm to deflect this tab. On this one, the pilot, puts the control input in through this arm and it moves this tab and causes the elevator to, the tab causes the elevator to move. On bombers during World War II, that was what they used since they didn't have hydraulics that they trusted. I think we had hydraulic brakes in World War II. However, I've got an airplane that was designed or built in 1946. Actually, it was designed in the 30s, called the Luscombe. Has mechanical brakes. They aren't worth a hoot. Okay, I'll be real honest with you. You kind of have to do the run-up on the roll when you have full brakes on and you're still rolling and doing your run-up on that airplane. Hydraulic brakes in the airplane industry is fairly recent. Even less, it's a little older than hydraulic operated controls, and of course now we're doing it electrically. Call it fly-by-wire, we're running electrons down the wire to a servo which moves the control. But this was a servo tab. The tab moved the control. On a B-17, that's how the pilots flew it. Was through this tab.
Yes, certainly. You're saying it's for bombers. Does that mean that this servo tab compared to the balance tab allows the pilot to use less force for maneuverability?
Yes, a lot less force because the aerodynamic load is only on this guy. Okay? So, the tab didn't need to be near as big as the elevator. It could be a lot smaller And you had a crew of two who could, if need be, could move that tab, and that moved the elevator.
Once the elevator deflected though, wouldn't there still be a large aerodynamic force on the?
On the tab? Yes,
Yeah.
yeah, there's a tab, there's a load on the tab, but again, you know, you could use two hands on those airplanes, and you had two pilots. And part of the reason for having two pilots was to be able to move the controls, okay? So, but this is a servo tab. You don't see them much anymore except in museums. Because we've got newer and more efficient ways of doing it, but, you know, it's the way to do it. Now, spring tab. Spring tab is a version of the servo tab. In some cases, you put a servo tab on and you have too little control force. Okay, that tab is just it's so powerful that you ain't got, you know, you don't have quite enough control force to tell when you're off trim. So you can tailor that control force by adjusting the spring constant. Spring tabs were used on early jet airplanes. Two examples. When I was in pilot training, the Air Force used the T-33 as the second airplane that we flew. The T-33 had a spring tab in the elevator circuit. It had hydraulic ailerons because the aileron forces were too high, but they said, no, we ain't gonna use hydraulics on the elevator. You know, the guy can use the rudder if he needs to, if the ailerons don't work quite right. But the other thing about the old T-33 was that the hydraulics in the ailerons, the stick had a deadband in it. And you could always tell a new student on his first flight in the T-33 because he went out waggling his wings at everybody due to that deadband there, because what happened, you move the stick a little bit and nothing happened, and so you moved it some more and then a lot happened. Okay, and then they went back the other way, see, and the next thing you know, they're a little, what we call a pilot-induced oscillation in the aileron mode. You could always tell when a new guy went out to fly the T-33 because that's what happened. After a while, he realized it and got used to it, and it, you know, went away. But the T-33 just had a irreversible system in the ailerons. It had a reversible system in the longitudinal, and to handle the loads, it used a spring tab. Now, there is a potential problem with any tab. It's called aerodynamic flutter. An aerodynamic flutter can destroy an airplane in less than 1 second.
Is this due to high frequency cycle fatigue or something like that, or?
No, the forces go out asymptotic. You may have seen there's a picture of a flutter incident with a bridge out in Washington. Have you seen that picture? You know, there's a picture in this bridge, you know, there's a big suspension bridge, and it's in a high wind and it destroyed itself. Thing of it is, it can happen very, very quickly. I'm here to tell you that because I have lived through that experience. My first airplane doing a dive test, at the dive speed, I bumped the elevator control with the heels of my hands, and there was boom in the back of the airplane. And the airplane started doing this. The outside loop. Right there, the left wing failed, and then things really got wild.
Did you check or something like that?
No, there was no ejection seat. I had to make my own hole, because the door wouldn't come off. And when my parachute opened, my feet weren't as high as the ceiling. And a touchdown was, jumping off of this table would hurt more than a touchdown. I landed in the edge of a cornfield. I was on the retract of the parachute. When a parachute opens, it stretches, the nylon risers, and you get pulled back in. And I was being pulled back in as I touched the ground. But we put a half horizontal tail in the tunnel out at that time, what was the B1 division of Rockwell out in Los Angeles, now Boeing. And this was a flutter tunnel that had an automatic shutdown device that when it sensed the flutter to start, it would shut the tunnel down. Well, in the case of this tail, it wasn't fast enough. Tail went down the tunnel, did $1 million worth of damage to the tunnel. However, I had said after the accident that what I had experienced was explosive flutter. And at the time, Rockwell had a number of folks that were World War II types, designers and what have you. One of the guys on the accident investigation board was the chief designer for the P-51 Mustang. And another fellow was the controls designer on that, and he said, there isn't any such damn thing as explosive flutter, which is what I called it. And he was in the tunnel that day when it went down the tunnel. He now believes in explosive flutter. But, so it can happen. We went down the tunnel, in the tunnel we had a high-speed movie camera. And by high speed, I mean 2,000 frames per second. That camera captured 120 frames of film. Knowing the startup time on the camera and those kinds of things, they were able to determine that this flutter started and went away in 0.3 of 1 second. So you don't want to have a flutter experience if you can avoid it. Okay? So that's the problem with tabs. And so you approach them very gently. This particular airplane that I had to jump out of after I died and went to heaven and all those sorts of things. That particular airplane had a full span leading balance tab. Full span on one side, not the other side. I wanted them on both sides, and that's how the airplane today, the final design, has tabs on both, leading balance tabs on both sides. But not full span, only, normal kind of trim tab size. But sometimes, have to learn the hard way. Well, here's the spring tab. See, in this case, again, this is still a pivot. We've got springs here, so you move this control while it compresses or stretches the spring and moves the tab. That's the spring tab. Again, that spring has a frequency. And so you have to make sure that frequency doesn't get together with other airplane frequencies and cause flutter. Structural dynamics, they call that. Some of you have probably taken a structural dynamics course. Quite complicated stuff. Mathematically very complicated, and that's why I have found over the years there's only certain flutter engineers that I trust. After they tell me the airplane's okay, I'll get in the airplane and do dive tests. otherwise not. Okay, spring-loaded tab. Well, spring-loaded tab is loaded in the up position so that it floats the elevator down like the down spring. Here's a picture of one. Okay. It provides the benefits and drawbacks of a down spring with one additional, and that's flutter. And as a result of the flutter tendency, you don't see them very much in use, but it's a possibility. Okay, aerodynamic balance. Well, like I say, we're getting more complicated as we go here, all right? Fairly easy to change a tab or change the control system to move the tab differently. You know, the simplest thing are the springs and weights. Next more complication is the tab. The last complication is changing the surface area of either the elevator, the stabilizer, or both. Several different types of aerodynamic balance. We have an overhang balance or setback hinge, and we'll talk more about each of these. We have horn balance, which is kind of these two are kind of the same. Internal balance with a flexible seal, a blunt trailing edge or a bevel trailing edge, and I'll give you some examples on some of these. Overhang balance is a controlled surface area ahead of the hinge line. Here's an example. Here's the hinge. Notice that we have a lot of surface area ahead of the elevator hinge. So the span or the chordwise lift distribution is going to affect the floating tendency of the elevator. It tends to reduce the floating tendency, which is what we want to do, and that's caused by the chordwise pressure distribution on the surface. Notice chordwise. Well, this is a pretty difficult change because essentially you're redesigning the elevator if you move the hinge, right? And so it's likely one of the last things we'd probably try. Horn balance, on the other hand, is fairly easy to do and does essentially the same thing that the setback hinge does. And horn balance is this sort of thing. We put all the area ahead of the hinge out here on the tip. And there's two types. We have, this is called shielded balance. And if you ran that all the way forward, that's unshielded. Some folks like it shielded because they say if it's unshielded and you're in icing, you may lock up the elevator. Well, that's not necessarily so. But if you go look at a Piper Navajo, there's one, sometimes the folks out at the hangar do maintenance on one. There's been one in there fairly recently. If you look at the elevator on it, it has horn balance, and it's got a flexible portion up here. The purpose is to be able to break ice falls. Okay, that flexible portion, the pilot, does one of these things, he can break any ice that might have accumulated on it because it isn't always going to fly in line. At certain times, the horn's going to be sticking up. And sometimes you'll get ice on it. So anyway, that's the horn balance. And two types, shielded and unshielded, which we talked about. Same as the overhang balance, but it's more often used as a flight test fix than overhang because it's physically easier to do. And let me show you an example here. Here's that little MECO airplane. Notice we did two things here. Originally we didn't have horn balance, so we cut that tip, sawed a chunk of that tip off, okay? And it put a piece, extended the area, and you can see this piece in here. So we got a bigger tail, which helped, because what does that do? larger tail volume moves the stick fixed neutral point aft, right? So we benefited from that, but for stick free, this horn balance helped, okay? So that was, here's a flight test fix. You'll see this on several different airplanes, okay? It may not, this one was unpainted, of course, the airplane was originally painted and then we found out we had to fix it. That's you, and that isn't uncommon, by the way, in industry, okay? Because the first thing that happens, the sales guys, they want pictures of the prototype, They can go out and sell it, man. And so the airplane will be painted. In fact, when I worked at Rockwell on the Air Commander 112, we had a first flight of the airplane, and then we had a first public flight of the airplane. The first flight was done with a green airplane, and I've got a picture of that was taken after that flight. It was done with, the airplane was all aluminum, and then it went to the paint shop and was painted for the first public flight, and they invited all the biggies in and what have you. And that was the airplane that came apart in flight. But so anyway, seeing this sort of thing is not uncommon in the real world. That's all I'm saying. Okay. So that's the horn balance. Another type of balance, internal balance. We're about to run out of time here. Internal balance with a flexible seal. And may look something like this. What this prevents from happening, and this one probably will give you a little better drag because you don't have high pressure area from one side of the surface plane to the other. It blocks it off from doing that, okay? But it also acts as a balance that, tends to reduce the floating tendency. The next one I have, the blunt trailing edge, form of aerodynamic balance. So it's like this. And it can fix, there's two types of short period. There's short period airplane, short period elevator, where the elevator will sit with a limited oscillation. It's not flutter, it's just a limited oscillation. Worked on a project once that had that kind of thing, and what we did to fix it was put 1/4-inch wedges on the trailing edge, one on top and one on the bottom, each side of the elevator, and it stopped the problem. Fairly simple change to make. Flight testing may be a little bit difficult to tailor it. You may have to work on several sizes of the wedges. The blunt trailing edge. And another one is the bevel trailing edge, and it's used to reduce control forces. The other one was used to increase them and stop short period problems. This one is used to reduce forces, and here's an example of it, the bevel trailing edge on the elevator. And if you ever see a Mooney airplane, I want you to go look at the ailerons. The ailerons on a Mooney have a bevel trailing edge. And it was to reduce the aileron forces, which were too high on the airplane to start with. Again, a flight test fix, and a flight test fix, well into the program. And this bevel trailing edge is, means a new aileron, but that's better than a whole new airplane. Okay. All right. Well, all of these simple stability augmentation systems can be used separately, together, and may save cost and complexity of a more modern system. So the next time you at the airport, see how many of these you can find. okay? See how many you can find. I think you'll be surprised, all right, at how many you can find, particularly if it's an airport where you have a variety of types of airplanes.